So hello and welcome. I'm Greg Johnston. I'm a Senior Application Specialist with Sensors and Software. Today I'd like to talk about some of the scientific details of the NOGGIN Ultra 100 GPR system that we recently introduced. A little bit of background before we get into it. Here's a slide showing the GPR antennas manufactured by Sensors and Software. We make GPR antennas with center frequencies from 12.5 megahertz on the low end to 1,000 megahertz on the high end. We make a variety of antennas because, as many of you know, low frequency antennas provide a greater depth of penetration, but with less resolution, while high frequency antennas provide greater resolution, but with less penetration. There are multiple applications for GPR. So the perfect system for your particular application is the GPR antenna that penetrates as deep as you need to see while resolving the objects or boundaries that you want to image. That's the perfect world. So if you are scanning concrete and only need to see 1 or 2 feet, you need a high frequency antenna with high resolution. On the other hand, if you're looking for geologic stratigraphy at depths of 20, 30, 40 meters or more, you're going to need low frequency antennas, perhaps 25 or 50 megahertz. One of the sweet frequencies in my experience is 100 megahertz. It is physically small enough, about 1 meter in length, to easily maneuver by hand, by towing, or by pushing on a cart. And it is useful for many applications: imaging geological structures, geotechnical applications like sinkholes, large, deep archaeological targets, and even finding deep utilities. Here is the best 100 megahertz data that I have ever seen in 28 years of looking at ground penetrating radar data. Collected by Dr. Harry Joel from the University of Wisconsin-Eau Claire. This data was collected in the Upper Peninsula in Michigan near Lake Superior shoreline. Penetration is 50 plus meters. It is very rare to achieve such deep penetration with GPR, but this image shows that it can be done. This site obviously has little or no clay. GPR lines like this one are one reason why I like 100 megahertz antennas. Up until 2010, if you wanted to collect 100 megahertz data with a Sensors and Software GPR system, you needed to be using a pulseEKKO system. That's the one I showed in my first slide with all the antennas. The pulseEKKO system is very modular, but that modularity means it's a little more complicated to use. For example, the transmitter and the receiver have their own batteries and their own cables. We wanted to create a 100 megahertz system that was simpler and easier to use, more like our NOGGIN models. So in 2010, we introduced the NOGGIN 100 to go along with the NOGGIN 250, 500, and 1000. Now, you might be asking yourself, if we already have a 100 megahertz NOGGIN system, and we've had one for 10 years, why did we make a new one? In my mind, the biggest limitation in the more widespread use of GPR is the depth of penetration. Simply put, you cannot always see as deep as you'd like to with GPR. I think anyone who has ever used GPR has run into this limitation, probably on their very first day of using it. For example, here is some 100 megahertz data collected on sand. There's 5 or 6 meters of penetration. Not bad. We can see some dipping reflectors that are probably cross-bedding and some sub-horizontal reflectors as well. But what if we want to see deeper? Seeing deeper is what the NOGGIN Ultra 100 is all about. So how did we do that? This is not an exhaustive list, but here are the 3 main factors that control the depth of penetration with GPR. Electrical conductivity of the material, GPR transmitter power, and background radio frequency noise. Let's discuss these factors. The first is the electrical conductivity of the material being scanned by the GPR. The higher the electrical conductivity of the material, the faster it attenuates or absorbs the GPR signals as it travels through the material. In this animation, you can see this effect. Clearly, the GPR signals travels deeper in the soil with lower electrical conductivity on the left, compared to the soil with higher electrical conductivity on the right. Many of you know this more simply as clay is bad for GPR. The underlying principle of that statement is that clay has high electrical conductivity that limits GPR penetration, just like on the right. So if we want to see deeper with GPR, we need to go to sites with soils with low electrical conductivity, like the sands in Florida. Unfortunately, going to a different site with soil conditions that are more favorable for GPR doesn't work for most people. Academics may be able to choose a different site for their research work, but if you're a contractor being paid to survey a particular site, this is not a reasonable option. The second option to see deeper with GPR is to increase the GPR transmitter power. However, there's an issue there as well: emission regulations. In the USA, the Federal Communications Commission, or FCC, has regulated the radio frequency emissions of ultra-wideband devices such as GPR systems since 2002. In Europe, the regulations were implemented in 2005 by the European Telecommunications Standards Institute and updated by the International Telecommunications Union in 2007. Industry Canada added regulations in 2009. These bodies have put limits on the radio frequency emissions of GPR systems. That is why all GPR systems sold in the United States, Canada, and Europe must have a sticker on them that proves that they have been tested and they comply. The sticker also displays their FCC and Industry Canada identification numbers and that they conform to the European standards. Let's have a look at these limits. Here's a plot of the power limits from 1 megahertz to 10,000 megahertz, the range that includes all GPR devices. The vertical axis is power, expressed as equivalent isotropic radiated power in dB meters. Notice that the limits differ at different frequency ranges. They're shown by this black line and then over here, this red line. These show the limits. The GPR frequency range is shown here. Basically, I'm calling 10 megahertz to 1,000 or 2,000 megahertz. Again, here's a look at GPR antennas that generate these frequencies. It takes an antenna about 8 meters long to generate GPR signals with a 12.5 megahertz center frequency. When you have the length of the antenna, you double the center frequency. So 25 megahertz antennas are half as long, or 4 meters. 50 megahertz antennas are 2 meters long. 100 megahertz antennas are 1 meter long. And by the time you get to 1,000 megahertz, these antennas are only about 7 centimeters long. So the length of the antennas that generate GPR signals vary in length 2 orders of magnitude, from 8 meters to 7 centimeters. Here is the power spectrum of a 500 megahertz GPR antenna superimposed on the emission limits. It is the blue line. It peaks at 500 megahertz, as you'd expect, and has lower power levels at the frequencies above and below 500 megahertz. When the regulations came into effect and all GPR systems had to be tested to prove they abide by the regulations, here is the experience of sensors and software. Our 250, 500, and 1000 megahertz antennas passed with minimal changes to the hardware. This is because they are shielded, and shielding limits the energy that gets out into the air. It is important to remember that the power of radio frequency emissions into the air is what the regulations are all about. These regulatory bodies don't care about how much power goes into the ground, just the amount that radiates into the air and could affect other radio communications. So high-frequency shielded GPR antennas were not greatly affected by the emission regulations. That was certainly good news for the GPR industry and high-frequency shallow applications like utility locating and concrete scanning. The regulations, however, hit low-frequency GPR systems harder. The main reason is that these antennas are not shielded, so there are more radio frequency emissions into the air. For our 50, 100, and 200 megahertz antennas to conform to the regulations, we had to reduce the GPR transmitter power from the power levels that we used in the 1980s, 90s, and early 2000s. Now, Sensors and Software also has 12.5 and 25 megahertz antennas. The result of the regulations is that we no longer sell those antenna frequencies into countries that regulate GPR emissions. The reason is that in order to conform, we would need to drop our GPR transmitter power so low that we could not excite the dipole antennas enough to propagate GPR signals into the subsurface. The data is just not viable. So the idea of increasing GPR penetration depth by increasing the transmitter power is just not going to happen in the current regulatory environment. This leads us to the third option, and the one we chose for the NOGGIN Ultra 100 system, reducing the background radio frequency noise so that we can detect weaker, deeper GPR signals. Let's discuss this idea. Here is a 100 megahertz line collected at the University of South Florida. Let's discuss the radio frequency signals that this GPR line consists of. The top of the section is the background random radio frequency noise present in the survey area. This is a combination of radio stations, TV stations, cell phones, radio communication by walkie-talkies, and many other sources of radio signals. These are recorded by the GPR receiver. Then the GPR transmitter fires, and the strong direct pulse of radio energy, way stronger than the background noise, is recorded by the GPR receiver. After that, the reflected GPR signals from the subsurface arrive at later and later times and are recorded by the GPR receiver. The reflected signals get weaker and weaker because of the attenuation of the signal as it travels deeper into the subsurface. Eventually, the GPR signals are the same strength as the background random noise. That is the depth of penetration. After this point, again, only random noise is recorded by the GPR receiver. Now, let's look at this again with different graphics showing the amplitude of the signals. When the GPR transmitter fires, there's a large spike in radio signal strength. This is shown in blue here. As time increases downward, the reflected GPR signals are recorded by the receiver, but they are attenuating and decreasing in strength at depth. Eventually, they fade to zero amplitude. But wait a second. Why is this red line the depth of penetration? And we can clearly see this on the cross-section. Why is this red line the depth of penetration when there's still GPR signals present below this line, as indicated by the blue section over here? The answer is because of the random background radio frequency noise. So the depth of penetration is not when the GPR signals attenuate to 0. The depth of penetration is the depth at which the GPR signal amplitudes, shown here in blue, decrease to the same level as the background noise floor, shown in yellow. Since there are GPR signals buried below the noise, this means that the depth of penetration will increase if we can decrease the noise floor. So watch this little graphic here, this little animation that shows this. Depth of penetration increases if we can drop the noise level. And this is the idea behind the NOGGIN Ultra 100 system, reducing the random noise to increase the depth of penetration. So how do we do this? We do it by stacking or averaging the data. So let's talk about what stacking can do for us. Okay, here's a typical GPR cross-section consisting of dozens, hundreds, or even thousands of vertical strips of data we call traces. We usually look at GPR cross-sections in colored or grayscale plots with the trace data interpolated to show a nice smooth image like this one. The reality is that each trace was collected at equal intervals across the surface, what we refer to as the step size. Here's a GPR cross-section plotted without interpolation. So you can see the pixelation caused by the data collection at discrete points on the surface. Back in the olden days, before we had color or even grayscale printers and monitors, data traces were plotted in a format called wiggle trace. Not too many people are used to looking at GPR data as wiggle traces anymore. But the reason I'm dragging you down memory lane is because wiggle traces are the best way of showing what stacking data can do. When a GPR system fires the transmitter, the signal's recorded. Stacking means that rather than just recording the signal every time the transmitter fires, we allow the transmitter to fire multiple times at one location, averaging the traces, and record only the average trace. So if we stack data 2 times, we fire the transmitter once, save the trace, fire the transmitter a second time, save that trace, then we average the 2 traces and record the average of those 2 traces. If we stack 4 times, we fire the transmitter once, save the trace, fire again, save the trace, fire again, save the trace, and fire a 4th time, save the trace. We average those 4 traces and we record the average of those 4 traces. And not surprisingly, we do exactly the same thing at 8 times. And this is exactly how it's done, up to thousands of stacks. Stacking traces multiple times and saving the average trace lowers the amount of noise, shown here as red signal in the average trace. The more you stack traces, the lower the noise, the better the GPR signal, and the deeper the depth of penetration. So here we can see that compared to 1 stack or 2 stacks, the amount of noise has reduced by the time we get down to 8 stacks, improving our data trace. Here's another way of showing this concept, perhaps a better way, because it shows what actually happens when you're collecting the data. If you're collecting data with a Noggin 250 on a smart cart, like we're showing here, it would look like this. This is data collected at 1 stack, really no averaging. We're just recording the trace as every trace that comes in. Here is what happens when you stack it 4 times. Notice the average trace of the 4 traces collected has less noise. Let that one, I want this one to animate again so that you can see what's actually happening as you go along. Stacking GPR data traces might not seem to do much, but the effects can be enormous. Let's delve into the math a little bit and quantify what stacking does to the random noise in a GPR trace. Okay, mathematics says that the amplitude of the random noise decreases by 1 over root n, where n is the number of stacks. That's what this table shows. For example, one stack means that 100% of the amplitude of the random noise is present in the recorded trace. 4 stacks reduces the amount of noise to 50%, 1 over root 4. 16 stacks reduces it to 25% of the noise. At 100 stacks, the noise has been reduced to 10%. That's 10 times smaller, or 1 order of magnitude. At 10,000 stacks, the noise is reduced to 1%, 100 times smaller, or 2 orders of magnitude. Since there are GPR signals buried below the noise, this means that if we can decrease the noise floor, we can see those weaker, deeper, real GPR reflectors. This idea is shown in this animation of 250 megahertz data collected by a master's student at the University of Arizona. A professor had buried a flat metal plate 3 meters in the ground many years before, and the geophysics students collect data from various geophysical instruments to try to detect that plate. Now, some of you may know that Arizona soil is generally not very good for deep GPR surveys. It tends to be very electrically conductive, which attenuates the GPR signals before they can travel very deep. But this example shows the power of stacking GPR data. At 1 stack, the depth of penetration, eyeballing it, is about 1.8 meters or so. But by about 512 stacks, the depth of penetration is increased to about 3 meters, and we start to see the metal plate. Beyond that, by 1,024 or 2,048 stacks, we have a good image of the metal plate and lots of confidence that that is a real subsurface object. All sensors and software systems, since the pulseEKKO 4 introduced in 1988, have had the ability to stack data up to 2,048 times. The problem was that stacking more than about 64 times took time. We're talking spending 5, 10, 60 seconds at each sample point on the ground. And even though it clearly makes the data better and increases the depth of penetration, most people do not have the patience to collect GPR data like that. The innovation in the NOGGIN Ultra 100 is now that we can stack up to 65,536 times and much faster than ever before. So high stacking to see deeper is much more practical than ever before. Let's look at some case study examples of data collected with the NOGGIN Ultra 100. One of our test sites during the development of the NOGGIN Ultra 100 was a set of buried concrete sewer pipes not too far from our office. This photo is not the actual pipes, but it shows the concept. On the left, NOGGIN 100 data collected at 4 stacks. On the right, NOGGIN Ultra 100 data collected at 512 stacks. Clearly, there is much higher data quality and depth of penetration at 512 stacks. The other good news is that both systems were collecting at the same speed, 14 kilometers per hour, or about 4 meters per second, a fast running pace. Now, I want to explore this data quantitatively. So I want to put some numbers to the amplitude type plots like the one I showed you earlier, like this one. In this plot, we can see the noise floor as the flat area before the GPR transmitter fires. And then we also see the noise floor as the area after the GPR signal attenuates back down. In both cases, they reach a noise floor here. If we compare the noise floor values at 4 stacks, here in the green line, and 512 stacks in the red line, we see that the noise floor has dropped from about 0.2 millivolts at 4 stacks to 0.03 millivolts at 512 stacks. So the noise floor is about 7 times smaller. We also see that the depth of penetration, defined as when the GPR signals attenuate down to the noise floor, increases from about 60 nanoseconds at 4 stacks to 90 nanoseconds at 512 stacks. So the penetration is actually increased from maybe 2 meters to 3 meters, which is a 50% increase in the depth of penetration by stacking. Let's look at the plots with a higher number of stacks, 4,096. Clearly, again, the higher number of stacks has improved the data quality. The noise floor in this case has dropped from 0.2 millivolts to 0.01 millivolts and has decreased about 20 times. And the depth of penetration has gone from about 2 meters to 4 meters, a 100% increase. Now, I should mention that because we are now collecting such low amplitude reflections, we had to increase the number of bits per point from 16 to 32. So the NOGGIN Ultra 100 system is a 32-bit system. All right, let's go to case study 2, which was collected at a site with glacial beach deposits. Here you can see the location of the survey. It's on the shoreline of glacial Lake Algonquin, which is the predecessor of modern-day Lake Huron. This is where we conduct our annual 3-day GPR course. It's an hour north of our office, and we go there because the soils are sandy, very favorable for GPR, and a great place to learn about GPR. Here's an animation of the NOGGIN Ultra 100 data from 4 stacks to 65,536 stacks. You can watch the depth of penetration increase with every slide with more and more stacking. Here are the noise floor plots. This time it shows all the noise floors from 4 stacks in red to 65,000 stacks in pink. As the number of stacks increase, we see the gradual drop of the noise floor amplitude predicted by the 1/square root formula. The noise floor at 65,000 stacks is 100 times smaller than at 4 stacks. So we've gone from 0.2 millivolts to 0.002 millivolts, 100 times smaller. Coupled with that, the depth of penetration is increased from about 5 meters to more than 15 meters, a 3 times increase. I just wanted to point out something kind of interesting in the data. See the amplitude bump here at about 140 nanoseconds? This is from a strong flat-lying reflector at that depth. This plot says that we cannot see it at 4 stacks, that it's below the noise level. So it takes about 32 stacks before we start to see it and the noise level drops. Here's a plot of 4 stacks versus 65,000 stacks. Clearly better data at higher stacks. I should point out that the 4 stack data was collected at 14 kilometers an hour, while the 65,000 stack data was collected at 0.2 kilometers per hour. So extremely high stacking does require the user to slow down. But to give you an idea of data collection speed, here's a table comparing the number of stacks collected by the NOGGIN 100 versus the NOGGIN Ultra 100 at various speeds. Fast running, or probably more likely towing at 14 kilometers an hour, provides 4 stacks from a NOGGIN 100 and 512 stacks from the NOGGIN Ultra 100. Walking at 3.6 kilometers an hour or just over 2 miles an hour provides 16 stacks from the NOGGIN 100 and 2,048 stacks with the NOGGIN Ultra 100. A slow walk increases the number of stacks from 32 to 4,096. Baby steps increases the number of stacks from 128 to 16,000. Based on the extreme speed of the NOGGIN Ultra 100, we have set the minimum number of stacks to 256 times. It just seemed pointless to allow the user to collect fewer stacks and have all that dead time when no traces were being stacked. This is a good time to point out that the NOGGIN Ultra 100 is the first product we have that marries the ultra stacking technology I've been describing here with our patented DynaQ technology. DynaQ is short for dynamic quality. And what it means is that when you are collecting GPR data on a system with an odometer wheel, like the Smart Cart or the Smart Toe configurations, you don't have to ever set the number of stacks to a fixed number such as 256. Rather, you set the stacks parameter to DynaQ and let it look after the stacking. Some of you will be familiar with DynaQ from our other products that have it. DynaQ is the colored bar under the GPR line as you collect the data. The color of the bar is an indicator of the number of times the trace above it was stacked. So when DynaQ does its automatic stacking, it stacks the data as many times as it can while you push the system. In this example, it is stacking 4 times during each step size. This shows the idea, but remember that the actual number of stacks will start at 256 stacks and go up to a maximum of 65,000 stacks. Difficult numbers to try to show in a simple animation like this one. With DynaQ, you only need to walk slower to increase the data quality and increase the depth of penetration. I want to emphasize that stacking only reduces signals that are truly random. If you have signals that are coherent, like the high-frequency external radio signals visible in this GPR section, stacking will not reduce the amplitude of this signal. In fact, stacking coherent signal will enhance it. By the way, I know that this is external radio frequency noise because the coherent signals are visible at the top of the GPR section before the GPR transmitter fires. Sensors and software systems always start recording signals before the GPR transmitter fires. So this is why that along with stacking, you want a GPR system that is quiet, because most coherent signal is actually generated by the GPR system itself. Have you ever seen bands through your GPR data like these ones? These are not real subsurface reflectors. In one case, this actual band in here, this is actually a subsurface reflector. These bands down here are not. These bands here are not. These are not real subsurface reflectors. I've seen lots of people interpret them as real subsurface reflectors, but they're not. One of the things I emphasize in my GPR training courses is that not all the signals you see in the GPR data are necessarily from the subsurface. And it's critical for GPR practitioners to know the difference. In these examples, the horizontal banding could be caused by the GPR system. The bands are caused by poor GPR design, with energy leaking onto metal cables or metal housings and re-radiating the GPR energy. So stacking is useless if your GPR system is generating a lot of coherent noise. You should always be looking for quiet GPR systems. The best way to test the signal that your GPR system produces is not to go to a good site, but go to a bad site for GPR. At a site with sandy soil that's good for GPR, almost any GPR system is going to perform well because the bad coherent system noise, shown in red in this image, is buried by the strong GPR reflectors, and so it's never seen. Go to a site with a heavy clay soil that attenuates the GPR signal quickly. Collect some data and see what you see. After the real GPR signals are attenuated to the background noise, is the signal random or is it coherent? If it's coherent noise, question the source of that noise. The last case study I'm going to show you is using the NOGGIN Ultra 100 to detect pipelines. The signs on the edge of the road here indicate where the pipelines are located, but we wanted to find them a couple hundred meters away in an open field. Here are the plots of the NOGGIN Ultra 100 data from 256 stacks to the maximum of 65,000 stacks. 256, 512, 1,000, 2,000, 4,000, 8,000, whoops, 16,000, 32,000, 65,000. So again, let me go through that. I'll go back down to 256 and back up to 65,000. Here are the plots of the 256 data on the left and the 65,000 stack data on the right. Clearly better data at higher stacks. At 256 stacks, we can see a hint of a deeper hyperbola, but we would be gutsy and probably very uncomfortable to say that it's a third pipeline. But at the higher number of stacks, the hyperbola is so strong and obvious that we'd have no problem making that interpretation. So in summary, the Ultra receiver increases GPR penetration by stacking thousands of times to reduce the random noise floor to reveal weaker, real GPR signals at depth. You get the high stacks with little or no reduction in the speed of data acquisition. In some cases, the depth of penetration has more than doubled when we compare it to the original NOGGIN 100 system. And so we think this is a great advance for the GPR community craving deeper penetration. I will add that I think my audience is eager to see more geological examples, as that is what 100 megahertz GPR systems are typically used for. I am too, but between the winter and COVID-19, we just have not gotten to these sorts of sites. And that is something that I am eagerly awaiting. So those of you who have a NOGGIN Ultra 100, please take it to some cool sites, send me the data because I would love to see how it performs. So that's it for today. I hope that you found the information on the science around the NOGGIN Ultra 100 useful. Thanks for attending, and watch your inbox for details of our next webinar. Okay, what is the maximum distance between the ground and the antenna? To get the maximum amount of GPR energy into the ground, you want the antenna to be within 1/10 of a wavelength of the surface. So a 100 megahertz antenna puts out a wavelength of about a meter, meter and a half. So you want to be maximum 10 to 15 centimeters from the surface at 100 megahertz. And you're starting to see more and more people who are putting GPR systems onto drones and collecting data. Couple points about that. One, in most countries, Canada, the United States, and Europe, it's not actually legal. The regulations say that ground penetrating radar systems must be used within 1 meter of the surface. So if somebody's flying around 10 meters, 20 meters, 50 meters above the surface with a GPR system, they are not abiding by the regulations. Now, if you are flying within a meter of the surface, then that is legal and can be done. But When you get those antennas way off the ground, the amount of energy that gets into the ground is going to drop dramatically. You're going to have two things going on. You've got the huge reflection coefficient of the ground, which can eat up easily 40 to 70% of the energy will reflect off the surface. And so that's less energy to go into the ground. Once the energy gets into the ground, then it starts attenuating. The other thing is the higher you are, the more spherical spreading there is of the signal. So the amplitude of the signal is dropped as well. Okay. Does stacking improve vertical resolution? No, we're not going to see an increase in vertical resolution. What is the limiting factor for the number of stacks, if stacks possible? There is no limiting factor, actually. We could collect stacks forever until the battery runs out or something like that. So there's really no. We picked 65,000 stacks in this particular case because you still have to go fairly slowly at 65,000 stacks. Right now, we can still go fairly quickly at 8,000, 16,000 stacks, but by the time you get up to 65,000, it's getting slow. So if we increased it to, 1 million stacks or something like that, it would just take more time. Okay, and the one thing we've learned over the years is that people aren't willing to spend that time, at least most people. The question is, may I know what kind of technology you guys are using? Is it pulse or real time? We do pulse the energy into the ground, and then we are real-time sampling. So yeah, another way, I think other people have called it real-time sampling. If you get to the details of a way a GPR system works, and most people don't sort of realize this, is that the older systems work by essentially strobing. So you'd fire the transmitter, and say you were collecting a trace that had, say, 500 points in it. You'd fire the transmitter once and you'd collect 1 point. You'd fire the transmitter a second time and you'd collect point number 2. Fire it a third time, collect point number 3. And so, in other words, to build up the trace once, you actually fired the transmitter 500 times. And now if you want to stack, say you want to stack 4 times, well, that means you now have to fire that transmitter 2,000 times in order to collect those 500 points 4 times. So the big change here is that we are not collecting one point at a time. We are collecting hundreds and thousands of points at a time. So when the transmitter fires once, we collect thousands of points. And that's where the speed is. And that's the difference between the older systems. So yes, it is called real-time sampling. Question, I would like to ask for the difference between pulseEKKO Ultra receiver, NOGGIN Ultra. Is it the same principle? Yes. Yeah, we introduced the Ultra receiver technology in the pulseEKKO system. We have the pulseEKKO Ultra receiver. We introduced that about 2 years ago. And now we have that same sort of technology in the NOGGIN 100. How do we know we're skipping data? Our systems will always tell you when you're skipping data. So if you're going too fast for the system to keep up, the system usually beeps at you. There'll be an indication by the DynaQ bar on the bottom of the screen. The DynaQ bar will go white. So if you actually go so fast that the system is not even able to collect and stack the data once, you will get a white spot in your data. And so what it actually does, what it really does, is it doesn't leave a blank spot in your data. It uses the last trace that it successfully collected and it fills that gap in. So what will happen is your data will start to pixelate because you're not really collecting at the normal interval. You're collecting at a larger sampling interval, larger step size. So that's what happens when you start to go really fast. Is there any chance to get unstacked raw data, for example? I guess the way I would do that is I would set it to 1 stack, because that's really unstacked raw data. So set it at 1 stack and set the system flying. And that's about the only way you can do it. Otherwise, we don't actually, if we stack data, say 8 times, we do not any longer have those 8 traces that were collected to make the one trace. They were not recorded. They were recorded long enough to average them, and only the average trace is saved. So hopefully that answers your question. Yeah, somebody actually noticed that during a walking scan, the antenna is not necessarily at the same location when it's stacking. And will that cause any issues? No, we found it hasn't really. So yes, technically you are smearing the traces across the step size. So for example, if you're using 100 megahertz, the default step size is 10 centimeters. So those 8,000 or 16,000 stacks are smeared over 10 centimeters. We have not found any issues with that. If you're an absolute purist, noggins do give you the ability to collect data at a single point and then move it. So you can collect at one point, move it. But our experience is that that's not worth the effort. Does Sensors and Software have units available for rent? Yes, we do. I'm not sure how many we have in the rental pool right now, but we do have at least one NOGGIN Ultra 100 system in the rental pool. And if you're if you're a university and you're interested in renting, contact us, let us know what your research is, and we'll see what we can do for you in terms of incentives. Can we identify a leakage of oil and water in an underground pipeline? Not exactly related to my webinar, but the short answer on that is that finding leakage from pipelines is tricky with GPR. You'll see a lot of studies that show that if you collect data over an area and then you introduce a leak to it, you can see the difference. You can see the properties of the subsurface change as whatever the material has injected into the soil. The problem is that in the leakage situation, you never have that before situation. You only have the after. So the data that you collect is only in the after state where, maybe there's a leak. And so there's no point of comparison to say, hey, wait, this area looks different than it did 2 months ago, and therefore maybe there's a leak there. And so you run into that difficult situation of trying to isolate or see a leak. And when water is introduced to the subsurface, it does change the velocity. And sometimes you can see that velocity change, but it's not that easy. Because the other thing is water is also affected by gravity. So when the water leaks out of the pipe, it often migrates downward. And so it's under the pipe. Whereas what you really want to see is if it was under pressure or something and it was forced upward in the leak, you might be able to see that velocity change. So in general, I tell people that ground penetrating radar is not necessarily the best tool for routinely finding leaks in pipes. Sometimes you have the right conditions that you can see changes that are obvious. Sometimes you can see the velocity variation, which may indicate a leak, but the vast majority of times you can't. Will stacking increase the depth of penetration in saline environments? If it's really saline, forget it. Saline environments, salt water absorbs, the GPR attenuation is in a centimeter. So even if you've got a wavelength of 1.5 meters, like the noggin, that signal is gone in a centimeter. There's no propagation of the signal. So I would say if you were in, maybe if you were in brackish situations where the salt is less than saline, then you're going to see an improvement there, may see an improvement in there, but pure saline, no. Now, what sampling speed does the system operate at 65,000 stacks? I'm trying to remember the number. I think it's 500 million points per second. That gives you an idea of the sampling speed. Can we get the diameter of rebars? No, certainly not. Well, not in general. GPR is pretty tricky. it's very difficult to pull diameter of cylindrical objects out of the GPR data unless those objects are very physically very large. So rebar, for example, we can't tell the difference between, small gauge rebar and large gauge rebar. You're not going to see that. And in general, the same thing on pipes. How accurate is the data taken from a boggy environment where the subsurface is a wetland? This is a place where high stacking can help. We can look in fresh water. GPR signal will penetrate through fresh water, but the more total dissolved solids that there are in the water, the less penetration you're going to get. So in other words, as the water becomes more saline, you're going to get a reduction in penetration. So if you're in a boggy environment, I've seen lots of data where, 5-10 meters through boggy environment, even more than that. So, I don't know the specifics of your situation, but I'd be looking at ground penetrating radar. It may be a useful tool.